Okay, welcome to lesson 1-5, infinite limits. So last week you learned that there were three different ways in which a limit does not exist. Remember, one of them is if, as x approaches c, the function approaches different values from the left and the right. A second way is if the function is unbounded, if it increases or decreases without bound as x approaches c. And then the third way was if the function wildly oscillates as x approaches c. Last week, we looked more closely at the first situation, which led us to talking about one-sided limits. Today, we're looking more at that second situation, where the limit does not exist because the function is increasing or decreasing without bound. So keep that in mind as we go through this lesson. To start with, we're going to start by reviewing a concept that you learned back in pre-calc. So let's consider this example here. So we're going to find the vertical asymptote, or asymptotes if there's more than one, of this rational function here. F of x equals 2x plus 6 over x squared minus x minus 12. So as you might recall, one thing that we want to do to find vertical asymptotes is we want to factor, because remember what we're really looking for are values of x that may make our denominator 0. But remember, there are also other types of discontinuities as well, such as a hole in the graph. So let's go ahead and start by factoring here. So let's factor out the 2 from the numerator. And then we can factor out the denominator into x minus 4 times x plus 3. So in this situation, as we can see, the x plus 3 factors will actually divide out, and that's going to give us a simplified form of 2 over x minus 4. So remember, what this means then is the graph of 2x plus 6 over x squared minus x minus 12 is going to behave the exact same way as this function here, 2 over x minus 4, except at negative 3. Remember, as you just learned a couple of days ago, at x equals negative 3, this function will actually have a hole in the graph. It will have a removable discontinuity. But at x equals 4, we have a non-removable or essential discontinuity. And for rational functions, that takes form as a vertical asymptote. So for this particular example, there's a vertical asymptote. At x equals positive 4. And we can see the same thing if we were to take a look at its graph. So this is what the graph of this function looks like. So once again, we've got this hole over at x equals negative 3, and we've got this vertical asymptote at x equals 4. So now that we've got the graph and the function, let's consider a couple of different limits here. So first, let's consider what happens to the limit as x approaches negative 3 of our function. Well, remember, if we were to substitute into the original function, we would have ended up with 0 over 0. Remember, that's an indeterminate form. But if we were to simplify the function, that would then give us the limit as x approaches negative 3 of 2 over x minus 4. And then now I can just use direct substitution, and that's going to give us a negative 2/7. So the limit as x approaches negative 3 for this particular function does exist. It's about negative 2/7, but just remember, at negative 3, there's actually a hole in the graph. But now, what about the limit as x approaches 4? Well, as we can see, as we approach 4 from either side, the function is either decreasing without bound as we approach 4 from the left, or the function is increasing without bound as we're approaching 4 from the right. So in either situation, this function is increasing or decreasing without bound. Therefore, the limit as x approaches 4 of this function does not exist. But we can be more specific about what's actually happening here from the left or from the right. So we can look a little bit more closely at the limit as x approaches 4 from the right side of this function. Well, again, as I was just saying earlier, if I'm approaching 4 from the right, notice that this function value is increasing without bound. For limits, we can say that that means that the limit as x approaches 4 from the right of f of x is positive infinity. Now, I need to try to make as clear as I can, I need to emphasize, this is still saying, so this still means that the limit does not exist. So remember, infinity is not a number. It's a concept. It's just implying that the value continues to increase without stopping. But we're able to be more specific about how this limit does not exist. We're specifically indicating that this limit doesn't exist because the function values are increasing without bound. That's all that the positive infinity is telling us. Similarly, we can talk about the limit of f of x as x approaches 4 from the left side. Again, if we go back to this graph, if I'm approaching 4 from the left side, we can clearly see that the function values are decreasing without bound. They're going downward forever. So in this situation, the limit of f of x as x approaches 4 from the left, we could say is negative infinity. And again, that still means that the limit does not exist, but we're just able to describe more specifically exactly what is happening here. So when we put that negative infinity, we're just saying that the function continues to decrease in value as we approach 4 from the left side. These two limits right here, where the limit becomes positive infinity or negative infinity, these are what we refer to as infinite limits. Okay, so let's look at another example here then. So let's let f of x equal 1 over x minus 2. We're going to find each of the following limits that I'm about to write, and we're going to specifically use positive infinity or negative infinity when possible. By the way, you may have noticed earlier that I actually put a positive symbol in front of that first infinity. That is not necessary. It's overkill. I was just trying to put it for emphasis. You are welcome to include the positive sign or not. Either way is fine. All right, so the first limit that we're going to find is the limit as x approaches 2 from the right of f of x. All right, so if I'm trying to find the limit of this function as x approaches 2 from the right, first let me go ahead and rewrite that function. So we're talking about 1 over x minus 2. Now remember, you learned last week that if you are trying to evaluate the limit analytically, we should be using direct substitution first. So if I use direct substitution, we do get 1 over 2 minus 2, which becomes 1 over 0. Now last week, you saw that this is not indeterminate form. 1 over 0 is not indeterminate form. This does tell us that the limit does not exist. Specifically, now that we are talking about infinite limits, we can actually say that when we have non-zero over 0 as the result of direct substitution, that this limit does not exist because of unbounded behavior. This function is either increasing or decreasing without bound. But because we are now discussing infinite limits, the expectation is that we actually analyze a little more closely so that we can state whether this one-sided limit is approaching positive infinity or approaching negative infinity. So we're going to investigate just a little bit further. So here's how we're going to do that. So I'm going to go back to this step right here. And let's go ahead and now substitute again. But instead of just putting a 2, I'm going to indicate that we're actually talking about substituting x with a number slightly larger than 2. Remember, that's what the little plus sign means, right? When we're saying x approaches 2 from the right. So what I'm really doing here is I'm substituting a value for x that's very close to 2, but slightly bigger than 2. Now, if I substitute a number very close to 2, but bigger than 2, and then I subtract the actual number 2 from that, that is going to give me, oh, I'm sorry, bad me. That limit should not be there anymore because I substituted. All right, so now, because I'm substituting a value slightly greater than 2, and then I'm subtracting the actual number 2 from it, that's now going to give me 1 over almost 0, but it's going to be slightly bigger than 0. Now, if you don't quite understand where I got that from, let's investigate that part just a little bit more closely. Remember, I just said in the denominator that I'm putting in a number very close to 2 but slightly bigger, so maybe 2.01. But then I'm subtracting 2 from that, so that's going to give me just 0.01. What if I got even closer? So 2.001 minus 2. Well, now that's going to be 0.001. So as you can see, if I'm approaching 2 from the right, slightly greater than 2, and then I subtract 2 from that, the result gives me a value that's very close to 0, but it's still positive, still greater than 0. So that's what this is indicating here. All right, so now, if you have a calculator nearby, what I'd like you to do is on your calculator, would you please do 1 divided by, and then pick whatever number you want that's very close to 0, but slightly positive. So 0.001, 0.00001, whatever you want. And then get even closer. Hopefully, after doing that maybe 1 or 2 times, you'll notice that the value you get is extremely large, but it's positive. So what that means then is this becomes positive infinity, because I have a positive number divided by a positive number, so that's why it's positive. And then it's infinity because I have a constant divided by a number extremely close to 0. Once again, I put the positive in front of the infinity just for emphasis. You don't have to put the positive. Okay, let's do another one here related to the same example. So now let's look at the limit as x approaches 2 from the left of that same function, 1 over x minus 2. So again, if I substitute in directly, I'm going to have 1 over slightly less than 2 minus 2. Now remember, if I'm substituting in a number that's slightly smaller than 2, and then I subtract a full 2 from that, it is going to give me a number very close to 0, but it's going to be slightly less than 0, which means it's going to be negative. So now I have a positive divided by a negative, which means I'm going to get a negative. And then again, because I have a constant divided by a number very close to 0, that's going to give me infinity. So therefore, this one-sided limit is negative infinity. And then finally, what if I'm looking for the two-sided limit as x approaches 2 of this function? Well, just like what you did last week, the one-sided limits do not agree. The one-sided limits don't agree. One of them in this case was a positive infinity, one of them was a negative infinity. Both of those are saying that the limit doesn't exist, but they're both describing slightly different behaviors. So because the one-sided limits don't agree, the best thing we can do for part C is to simply say that the limit does not exist. Because in this case, the function is increasing without bound as we approach 2 from the right side, but the function is decreasing without bound as we approach 2 from the left side. So if I'm discussing the two-sided limit, the best we can say is that the limit simply does not exist. All right, so let's look at another example similar to the previous one. So this time we're going to let f of x be 1 over x squared. Again, we're going to find each limit, and we're going to use positive or negative infinity whenever possible. So for part A, we have the limit of 1 over x squared as x approaches 0 from the right. All right, so if I were to use direct substitution, that is going to give me 1 over 0, which means that the limit does not exist. But again, that means now we want to see if we can be more specific about that behavior. Is this going to be increasing without bound or decreasing without bound? So if I were to do direct substitution here, that means I'm going to have 1 divided by a number very close to 0, but slightly greater, so it's positive. And then I'm going to square it. Now, if you take any number close to 0, 0.01, 0.001, and you square it, it's going to actually make that number even smaller. So squaring that is now going to become 1 over, again, a number very close to 0, but still positive, slightly greater than 0. So that means now I have a positive divided by a positive, and it's a constant divided by a number very close to 0. So this does become positive infinity. Okay, let's compare that now if x is approaching 0 from the left. So again, we're talking about numbers very close to 0, but because it's slightly less, it's actually now negative. So this is now going to become 1 over, again, a number slightly less than 0, which is negative, but then I'm going to square it. And when you square a negative, it does become positive. So this is now going to become 1 over something very close to 0, but now it's slightly greater than 0, so it's positive. So again, I've got a positive divided by a positive, and that's going to give us a positive infinity as well. So now, for the two-sided limit, since we know both of the one-sided limits are increasing without bound, then that means for the two-sided limit of this function, I can actually say that this will just be positive infinity, because we are now saying that no matter which side of 0 we're approaching from, the function values are increasing without bound. So very similar to last week when you were dealing with one-sided limits versus a two-sided limit. If the one-sided limits agree, then the two-sided limit is the same. But what I cannot emphasize enough still is that because we're writing infinity or negative infinity, we are still saying that the limit does not exist. We're just being more specific about how it does not exist. So once again, just to have it in writing, stating that the limit of f of x as x approaches c equals infinity or negative infinity still indicates that the limit does not exist. Okay, so let's look at a few examples now. So evaluate each limit, use infinity or negative infinity when appropriate. So for example A, we have the limit of x plus 2 over x squared minus 9 as x approaches 3 from the right. Now this one you can reason your way through otherwise, but as a general rule for rational functions in particular, you're going to actually want to factor, and you'll see why in just a moment. But we're going to actually factor here first. Sorry, I should actually back up. Again, we're going to use direct substitution first, but as you can see, that's going to give us 5 over 0, which does mean that the limit does not exist, but because we're talking about infinite limits, we do need to investigate more closely. And to do that, we're going to factor now. So if I factor this, I get the limit as x approaches 3 from the right of x plus 2, so the numerator doesn't factor, over x plus 3 times x minus 3. Okay, so now, if I were to substitute now, then that means we're going to have slightly bigger than 3 plus 2 over slightly bigger than 3 plus 3, and then slightly bigger than 3 minus 3. Now, the slightly bigger than 3 doesn't really matter anywhere except for the fact where we're subtracting the 3. So in other words, slightly bigger than 3 plus 2, that's still going to be slightly close to 5. Yeah, it's going to be slightly greater, but I don't really care. Mainly because whether I'm close to 5 from the left or from the right, it's still positive. Same thing here. 3 plus 3, that's going to be very close to 6. Yeah, it's going to be slightly greater than 6, but even slightly less than 6 is still positive. So this is still going to be very close to positive 6. But here's where it really matters. 3 minus 3, that's going to take us close to 0. But remember, because we started by taking a number slightly bigger than 3 and then subtracting 3 from that, that's going to be slightly greater than 0, meaning I actually have a positive value there. So if I have a positive number, such as 6, and then I have a number very close to 0 that's also positive. This is now going to give me 5 over a number very close to 0, but it's still positive, because a positive times a positive is positive. And finally, now I've got a positive constant divided by a number very close to 0, but it's still positive. So as you saw earlier, this is going to give us a positive infinity. All right, let's look at another one. So I have the limit as x approaches 1 from the left of x squared minus 3x over x minus 1. All right, if I use direct substitution, that's going to give me a negative 2 over a 0. And again, we already know then that that means this limit does not exist, but because we're talking about infinite limits, we need to investigate this a little bit more closely. So I'm now going to rewrite this function. So I have the limit as x approaches 1 from the left of x times x minus 3 all over x minus 1. So if I were to substitute, I'm going to have 1 times 1 minus 3 divided by 1 minus 1. But again, we're talking about a number slightly less than 1. So now in the numerator, I've really got 1 times negative 2 divided by, again, I had slightly smaller than 1 minus an actual 1. That's going to get us close to 0, but it's slightly less than 0. And so 1 times negative 2 is going to give me negative 2 divided by slightly less than 0. So that means I've got a negative divided by a negative. Well, a negative divided by a negative is positive. And then again, a constant divided by a number close to 0 gives me infinity. All right, let's do one more here of these kinds. So this time we've got the limit as x approaches positive 1 from the right of x plus 2 over x squared minus 4x plus 3. Okay, so once again, direct substitution. That would give me a 3 in the numerator. And in the denominator, I've got 1 squared. That's 1 minus 4, which is negative 3, plus 3, which is 0. All right, so I've got 3 over 0. I know the limit doesn't exist, but because it's a one-sided limit, I will be able to say whether it's an infinity or a negative infinity. So let's investigate more closely. So I have the limit as x approaches 1 from the right of x plus 2 over x minus 1 times x minus 3. So now when I substitute, I'm going to get a 1 plus 2 in the numerator. Down here I'm going to have 1, but again slightly greater than 1, minus 1, and then a 1 minus 3. So now I've got 3 divided by, so 1 slightly greater than 1, minus 1 is going to be 0, but slightly bigger. And then 1 minus 3 is negative 2. So now, look very carefully here. I've got almost 0 times negative 2. So again, that denominator is going to become almost 0. But I've got a positive times a negative. So suddenly, that sign is now going to switch. So now I've got a positive 3 in the numerator, and in the denominator, I've got a number that's very close to 0, but it's now negative. It's slightly less than 0. So that means now I've got a positive divided by a negative, which we know it becomes a negative. So we end up with a negative infinity. All right, so now that we've seen some infinite limits, that does mean that we want to make sure that we know how we can deal with those if they're used in conjunction with other types of limits. So we do have some properties for infinite limits as well, and these are sort of an offshoot from the properties of limits that you learned last week, so we can add on to the properties that you already know. So the first one looks like this. We have the limit of f of x plus or minus g of x as x approaches c. Well, that's going to actually be infinity. And let's think about why that is. So last week you learned that if I have the limit of a sum or a difference of two functions, that's going to be the sum or the difference of their individual limits. So this is the same then as the limit of f of x as x approaches c plus or minus the limit of g of x as x approaches c. But remember, the limit of f of x is increasing without bound. It's infinity. And then I'm adding to that, or I'm subtracting from that, some number L. Well, if I have a value that just continues to get bigger and bigger and bigger, and then I just add or subtract a constant to that or from that, it doesn't really change the fact that this value is still getting larger. So adding or subtracting a constant value, it's like a minor blip in the road, or it's a bump in the road, and it doesn't really affect its overall trajectory. This is still just increasing without bound. Now, I do want you to notice, if this were switched around, if this were the limit as x approaches c of g of x minus f of x, I do want you to notice how that would change. This would now be L minus infinity. Now, if I have a constant and then I subtract an increasingly large number from that, that does become negative infinity. So just wanted to make sure that you saw that. All right. The second property deals with the product of these two functions. If I have the limit as x approaches c of f of x times g of x, well, remember, the limit of f of x was infinity. The limit of g of x was L. You also learned last week that if I have the limit of a product, that this is going to be the product of their individual limits, which means I've got an increasingly large number times a constant. Well, what do you think is going to happen there? And if you're thinking, well, it depends, you're right. It's going to depend on what that L value is. If L is positive, then that means this limit will be positive infinity. But if L is negative, then that means this limit of their product will now be negative infinity. Again, because we would be taking a positive times a negative, or a positive times a positive. Some of you may be wondering, what happens if L equals 0? As it turns out, and you don't have to think about this too much right now, but just so you've heard it, if L is 0, infinity times 0 is actually another indeterminate form. And this might not mean a lot to you right now, but I do need to clarify. This is only if the limit is 0. Okay? If you are actually multiplying an increasingly large number by the actual number 0, then that is still 0. That's the same rule that you've always known. But if the limit is 0, this is indeterminate form. Because remember, if we're saying that the limit is 0, we're actually saying it's just a number very close to 0. It's not necessarily actually 0. All right, one more property here. So this last property we've got, the limit as x approaches c of, now pay close attention to the order here, g of x over f of x. Okay, specifically g of x over f of x. Now last week, again, you learned that if you have the limit of a quotient, that's going to be the quotient of their individual limits. But we know that the limit of g is some constant L, and we know that the limit of f is increasingly large. Now again, if you've got a calculator nearby, go ahead and pause this video and do the following. Well, don't pause it yet. Go ahead and grab your calculator and just do any constant you want, so maybe like 5 or 12, and then divide it by a really, really big number. And then do the same thing by even bigger numbers. Hopefully, as you've done that, you saw that the result got closer and closer to 0. Okay, and then one final note here regarding these properties. So I already told you that infinity times 0 was indeterminate when 0 was an actual limit. But also, if you end up with an infinity minus infinity, that's also indeterminate. And sometimes people have a little bit of a hard time understanding why that's the case. Remember, infinity just means that the values are increasing without bound. But you could approach or increase without bound at different rates. So it's possible for infinity minus infinity to take on different meanings depending on how each of these values are increasing. Okay? All right, so let's wrap up here with just a couple last examples. So we've got the limit of 8 minus 1 over x as x approaches 0 from the left. And we're just going to, again, find each limit, and we're going to use infinity or negative infinity when possible. So for this one, again, because I've got the limit of a difference, I should be able to think about the fact that this is the limit as x approaches 0 from the left of 8 minus the limit as x approaches 0 from the left of 1 over x. As you saw last week, the limit of a constant is just the constant, so the limit of 8 is 8 minus, now the limit of 1 over x as x approaches 0, as we were just doing a few examples ago, this is going to be 1 over 0 but slightly less. So that means I've got a positive divided by a negative. So what I have then is 8 minus a negative infinity. Now again, even though infinity is not a number, negative infinity does mean we're dealing with negative numbers. And if I'm subtracting a negative number, that still turns into addition. So this is still 8 plus infinity, which means this is just going to be infinity, or positive infinity. Okay, and we're going to wrap up here with this last example that involves trig and these infinite limits. So we've got the limit of x plus 2 over the sine of x as x approaches 0 from the left. Okay, so again, if I use direct substitution, this is going to give me 2 over the sine of 0, which is 2 over 0. So again, we know that the limit does not exist, but this is going to be an infinite limit. So let's actually explore this whole sine of 0 thing a little bit more closely. So we know again that this is going to be 2 over the sine of something slightly less than 0. So there are two ways that you can consider this. One way that you can think about this is using your unit circle. Now in the unit circle, remember that this right here is your 0. And if I'm approaching 0 from the left, remember that means slightly less than 0, then that means we're really looking at an angle that's in quadrant 4. Now we know that in quadrant 4, remember that cosine and secant are your positive functions, and then sine and tangent are your negative functions. So because we're approaching 0 from the left, we are in quadrant 4. So sine of 0 sine of something close to 0 is going to be close to 0, but it's going to be negative because we're in quadrant 4. So this is going to become 2 over something slightly less than 0. So I've got a positive divided by a negative, and that does give me a negative infinity. Now, the second way that you could think about this, if the unit circle isn't quite your thing, which I know for many of you it's not, the other thing you could do is think about the graph of sine of x. So you learned how to graph sine of x back in pre-calc or math 3, depending. And remember, the graph of sine of x looks something like this. But remember, it continues its pattern. So same as what you've been studying, if I'm approaching 0 from the left side, well, as I'm getting closer to 0 from the left side, these y values are also getting close to 0, but they are below the x-axis, so we know that those values are negative. So again, that would justify that this is getting close to 0, but it's slightly below 0. All right. So again, infinite limits, can't emphasize enough. It does still mean that the limit does not exist, but we're just being more specific about how the function behaves. If the limit is positive infinity, then the limit does not exist because the function is increasing without bound. If we're using a negative infinity, we're saying the limit does not exist because the function is decreasing without bound.